Hey guys, welcome back. This is the 8th video in the series, which is the integration of a logarithmic function. Here we're going to learn how to integrate using the logarithmic function and something called U-substitution. Okay, so the log rule for integration. Let u be a differentiable function of x. The first rule we have is simply the antiderivative of 1 over x. And what we end up with is ln of the absolute value of x plus c, my constant. Now it's extremely important that we put the absolute value because we cannot take the log or the natural logarithm of a negative value. So that's why very often you'll see the absolute value. The second rule is similar to the first one, except it's u. So now remember that if it's a function other than x, we use u instead. So for example, if it was 1 over x squared, or 1 over x plus 1, or 1 over 3x minus 2, regardless, any one of those falls under u, so therefore will simply be the ln of the absolute value of u plus c. However, in this section, what we'll really be using is the alternate form of the log rule. And this is what it looks like. It's the antiderivative of u prime over u. So, if the question fits this specific rule, then all I have to do is simply take the ln of the absolute value of u and then add my constant. And once again, this is going to be the form that we'll see most often in this section. So if the function is in this form, then we simply use the alternate form. If it is not, then we try to modify the look of the function so that it does. And we've done that before where we've modified the look of a function. We did it in previous videos where we used the substitution method. And I'll be showing you an example of that a little bit later on. So first and foremost, we need to be able to identify the form. The first one, we have the antiderivative of 2x plus 1 over x squared plus x. Okay, it's a quotient, so far so good. Now, if I were to take the derivative of x squared plus x, I would end up with 2x plus 1. Excellent. It actually fits the form. However, for the second one, you can see that the denominator is x squared plus 1, and if I were to take the derivative of x squared plus 1, I end up with 2x, but my numerator is simply x, so therefore it does not fit the pattern. So therefore we need to modify the question so that we can. So let's take a look at some examples. Example number 1, and we saw this in the previous slide. So we have a quotient, we have 2x plus 1 over x squared plus x. You should realize that x squared plus x is actually u. So if I take the derivative of x squared plus x, I end up with 2x plus 1. Does it fit the pattern? Yes, it does. U prime over u du is simply ln of the absolute value of u. So all we simply have to do is find the antiderivative, which is the ln of the absolute value of x squared plus x, and then don't forget to add your constant. Now, sometimes what you'll notice is that they eliminate the absolute value and simply put round brackets. And the reason why they do this is because no matter what x value we choose for x, it'll always be a positive value. So therefore the absolute value in this particular case is not necessary. However, to be safe, always put the absolute value. You can't go wrong that way. The second example, we have 6x over 3x squared. Once again, it's a quotient. If I take the derivative of 3x squared, I end up with 6x. It fits the pattern, so simply the antiderivative is the ln of the absolute value of 3x squared plus my constant c. For the third example, a little bit different. It's a quotient again, and if I were to take the derivative of x squared plus 1, I end up with 2x. But my numerator is simply x, so we have something missing. We need to modify. So, since the derivative is x squared plus 1, or the derivative of x squared plus 1 is 2x, I know that I have to rewrite the integral. So I modify the look of it. And with all the other steps that we've done in the other videos, it should be quite easy now. It's 1/2 times the integral of 2x over x squared plus 1. In doing this, in modifying the look of it, now it actually fits the pattern. My u is x squared plus 1, so it's simply 1/2 times the ln of the absolute value of u, and therefore don't forget to add your c as your constant. So let's say you have a very difficult time modifying the integral. In other words, you always had difficulty trying to figure out what needs to be added to change the look of it. So we're going to look at an alternate method for students who have difficulty modifying the integral. So we're going to use the idea of the substitution method that we've done in previous videos. So let's take a look. So we're going to take the same example we just previously did, but this time we're going to use the substitution idea. So we're going to let u equal to x squared plus 1. We're going to take the derivative. I end up with du dx equal to 2x. So far so good. I'm going to cross multiply and solve for x dx because that's what I need. So now I'm going to rewrite the integral, but in terms of u. So I have 1 over u times du over 2. Now du over 2 is simply a half multiplied by du. So I have 1/2 times the integral of 1 over u du. So far so good. We know what the integral of 1 over u is. It's simply ln u. And u in this case is x squared plus 1. Final answer, 1/2 times the ln of the absolute value of x squared plus 1 plus my constant. So we can use the substitution method every time we're trying to find a way to modify the look of the integral. Okay, so let's move on to example number 4. We have the integral of x squared plus 1 over x cubed plus 3x dx. Now, if I were to take the derivative of x cubed plus 3x, I would end up with 3x squared plus 3. However, my numerator is simply x squared plus 1. So therefore, I have to find a way to rewrite the integral. And we simply have to multiply the integral by 1/3 and change the numerator to 3x squared plus 3. Because if I were to multiply 3x squared plus 3 times 1/3, I would end up with my numerator, which is x squared plus 1. So therefore, all I have to simply do is multiply ln u by 1/3. So therefore, 1/3 times the ln of the absolute value of x cubed plus 3x, and then plus my constant c. Okay, question number 5 is a little bit more challenging. Now I'm going to do this in one step, and then I'll do it again, the same problem, but using the substitution method for those students who are having a little bit of a difficult time transforming this mathematically. So, first thing I'm going to do is I'm going to rewrite the integral because I want a quotient. And because I'm taking x to the 2/3 and bringing it up to the numerator, it becomes a negative exponent. Okay, next I find the derivative of the denominator, and therefore I end up with 1/3 x to the negative 2/3. Okay, looks quite the same, however there's the 1/3 part that's extra. So therefore what I'm going to do is I'm simply going to rewrite this as 1 over 3 times x to the 2/3. In other words, bring the negative exponent down in the denominator, and rewrite my integral once again. Now what I want you to notice is that I'm multiplying the integral by 3, because if I multiply it by 3, I end up with, once again, x to the negative 2/3. So since the u prime is in the numerator, u is in the denominator, and therefore 3 times the integral, then I simply have to find the antiderivative, which is 3 times the ln of the absolute value of 1 plus x to the 1/3 plus my constant. Okay. So for those students who did not really see this or having a little bit of a difficult time figuring this out mathematically, let's use the substitution method. So once again, same problem. I'm going to rewrite it because I want a quotient. Remember what we want. We want u prime over u. And therefore, what I'm going to do is I'm going to let u equal to 1 plus x to the 1/3. I'm going to take the derivative and therefore end up with du dx is equal to 1/3 x to the negative 2/3. Now remember what I need? I need x to the negative 2/3 dx, which is simply 3 du. Fantastic. Now it's 3 times the integral of 1 over u, and we already know what the antiderivative of 1 over u is. So simply 3 times the ln of the absolute value of x of 1 plus x to the 1/3 plus my constant. Same answer, different technique. One just simply doing it, logically, and the other one using the substitution method. Okay, we're going to take a look at some examples using the process of long division. And yes, you heard right, long division. So we're going to use this process when the degree of the numerator is greater than the degree of the denominator. So let me show you a couple of examples. The first one, we have a degree of 2 in the numerator and a degree of 1 in the denominator, so therefore the degree of the numerator is greater than that of the denominator. In the second example, same idea, we have the degree of 2, so the degree of the numerator is greater than that of the denominator. And finally, the third example, we have the degree of the numerator is 3 and the degree of the denominator is 2. So once again, the degree of the numerator is larger than that of the denominator. Okay, so whenever we have a question, a quotient, okay, and we are looking to find the antiderivative, we're going to use the long division process for these specific cases. So, what is the process? Well, long division. Now, we need to write our answer in a specific form, and the form that we're looking for is the quotient plus the remainder over the divisor. So when we perform long division, I got to write down my answer as the quotient plus the remainder over the divisor. So I'm going to do these three examples with you. So let's get started. So we have x squared minus 3x plus 2 over x plus 1 dx. The degree of the numerator is greater than that of the denominator, so therefore I have to perform long division. So we divide, we multiply by x, I end up with x squared plus x, we subtract, I end up with negative 4x, bring down the 2, multiply by negative 4, negative 4x minus 4, subtract once again, I end up with a remainder of 6. So I need to write my answer in the following form: the quotient plus the remainder over the divisor. Okay, so far so good. Once I'm able to write in this form, all I need to do is simply integrate the two parts. So I take the integral of the quotient plus the integral of the remainder over the divisor. Once again, the 6 is a constant. I can pull it out. And now I have the integral of x minus 4 dx plus 6 times the integral of 1 over x plus 1. Okay, now if I look carefully at the second part, which is the remainder over the divisor, I can see that if I take the derivative of x plus 1, I get 1. So it fits the form of u prime. So all I need to do now is simply find the antiderivative of x minus 4 and find the antiderivative of 1 over x plus 1. And what I end up with x squared over 2 minus 4x plus 6 times the ln of the absolute value of x plus 1 plus my constant. Okay, so let's take a look at the second example. We have 2x squared plus 7x minus 3 over x minus 2. Once again, we have a quotient. We have the degree of the numerator is larger than the degree of the denominator. So therefore, through the magic of math, there's the form. We have the quotient plus the remainder over the divisor. Okay, we performed long division, and this is what we ended up. So we simply rewrite this as a sum of integrals. We have the first part, which is the integral of the quotient, plus the remainder over the divisor. Now remember that since we have a constant 19, I can simply factor out the constant, and therefore I can find the integral of the first part, and then we'll hold on for a second for the second part. So the integral of 2x plus 1 is simply x squared plus 11x, and then plus 19 times the integral of 1 over x minus 2. Now, if I were to take the derivative of x minus 2, I would end up with 1. So therefore, that integral fits the u prime over u, and therefore all I simply have to do is take the ln of the absolute value of u, and there we go. X squared plus 11x plus 19 times the ln of the absolute value of x minus 2, and then plus my constant. Okay, example number 3. X cubed minus 3x squared plus 4x minus 9 over x squared plus 3 dx. Once again, the degree of the numerator larger than the degree of the denominator. Let's perform or use the process of long division, and we end up with x minus 3 plus x over x squared plus 3. Now don't forget, you can always pause the video, practice long division. It's very, very important, okay, and see if you end up with the same answer. So here, once again, we break it up into a sum of integrals. We have the first part, which is the integral of the quotient, plus the remainder over the divisor. Okay, now this one looks a little bit different than the other ones we did. Now remember, if I were to take the derivative of the denominator, I would end up with 2x. But here, we only have x. So therefore, we need to modify the look of this part of the integral. So I rewrite the integral, and now it's going to be 1/2 times the integral of 2x over x squared plus 3. Rewrite, and simply find the integral. There you go. Okay, so we learned the technique of u prime over u, which we'll be using for this section. And of course, we learned the long division process when the degree of the numerator is larger than the degree of the denominator. Now here we have something called U-substitution. Now this is an important technique. It's a different technique, but we also use the logarithmic function for this one. So let's get started. we have the integral of 1 over 1 plus the square root of 3x. Now, the degree of the numerator and the degree of the denominator don't have anything to do with it, so it doesn't follow that particular pattern. And u prime over u, not necessarily. So this is what we're going to do instead. We're going to let u equal to 1 plus the square root of 3x. But now what I'm going to do instead is I'm going to solve for the square root of 3x and simply put u minus 1. Hold on for a second. I'll explain to you why we're doing this. So, we're going to find the derivative like we normally would for u, and therefore we get du over dx is equal to 1/2 3x to the negative 1/2 times the derivative of 3x, which is 3. We're going to simplify. We're going to cross multiply, and we're going to solve for dx. Now what I want you to notice is that we have the square root of 3x, but now we're trying to find the integration or the integral in terms of du. So we have a small problem here. So what we're going to do is we're going to substitute the square root of 3x with simply u minus 1. And that's where the u substitution comes in. Now we have everything in terms of u. So we rewrite by replacing everything in terms of u, and this is what I end up with. 2/3 times u minus 1 du over 1 plus, and instead of writing the square root of 3x, we know that the square root of 3x is equal to u minus 1. So we replace the square root of 3x with u minus 1. Now we have everything written in terms of u. All we have to do now is just simply simplify, reduce, and break it up. Now I have 2/3 times u minus the ln of the absolute value of u. Distribute the 2/3. I get 2/3 u minus 2/3 times the ln of the absolute value of u, and simply replace u with what we had previously, which is 1 plus the square root of 3x. Don't forget to add my constant, and there is the antiderivative. So this particular technique requires us to change everything in terms of u. And what I want you to notice, the issue arises when we have x and du on the same side of the equation. So therefore I have to substitute x in terms of u so that everything is written in terms of u. Let's do another example. Okay, so the second example, we have the integral of 1 minus the square root of x over 1 plus the square root of x. Once again, it doesn't fit really the u prime over u. It doesn't fit the degree of the numerator is larger than the degree of the denominator. So now what do I do? Well, we know we have a quotient. So I'm going to let u equal to 1 plus the square root of x. Now I want you to realize that this is similar to what we did in the previous example. So what we'll do is we'll simply solve for the square root of x, and we'll end up with u minus 1. So we're going to hold off for a second. We're going to keep that at the back of our minds, and we're going to continue with the problem. So simply take the derivative. I end up with 1/2 x to the negative 1/2. Rewrite it as 1 over 2 times the square root of x. Cross multiply and solve for dx. Now what I want you to notice here is that we have a square root of x and a du. So those terms don't agree. So therefore I need to substitute the square root of x with u minus 1. After I've done this, I have to make sure that when I integrate, when I find the antiderivative, everything has to be in terms of u. So this is what it looks like. 1 minus the square root of x becomes 1 minus u minus 1. And then of course the du part or the dx part becomes 2 times u minus 1 du. Over 1 plus the square root of x, but because we have to write everything in terms of x, it's actually 1 plus u minus 1. Okay, now that everything has been written in terms of u, we just simply simplify. We just simplify the expression. So 1 minus u minus 1 becomes 1 minus u times 2u minus 2. Simplify further. Simplify again. Distribute. And therefore we get something that looks a little bit simpler. So we end up with the integral of negative 2u plus 6 minus 4 over u du. Perfect. We break this up, or we factor out the constants. So I get the negative 2, which is factored out. I have u du, and then the 6 du, and then minus 4 times 1 over u. Okay. Now I simply find the integral of each part. So I get negative 2 times u squared over 2, the integral of 6 is 0, and then minus 4 times the ln of the absolute value of u. Now remember that we always write our answer in terms of x, so I simply replace u with 1 plus square root of x, and I'm done. So you'll notice that the process is quite similar. Remember that when we're using this technique, the U-substitution technique, we want to write everything in terms of u. Okay, so this question is a little bit different. This one is finding differential equations using logs. We have this differential equation, or we were looking for the differential equation. We're given that the derivative, dy over dx, is equal to x minus 2 over x, and this particular equation passes through the point negative 1, 0. Okay, so like we've done in past videos, all we simply do is we cross multiply. So we have dy is equal to x minus 2 over x dx. We take the integral of both sides, remembering that the integral of dy, or 1 dy, is simply y. So I end up with y is equal to the integral of 1 minus the integral of 2 over x. Remember that 2 is a constant. I can factor out the constant, and now simply find the integral of 1 over x. Therefore, it becomes x minus 2 times the ln of the absolute value of x plus c. Now remember, the plus c is a general, or this is the general antiderivative, but we know that this passes through a specific point, and it passes through the point negative 1, 0. Now this is why the absolute value is so important. So now that x is negative 1 and y is 0, I replace x and y with those values, and now I take the ln of the absolute value of negative 1. You see, if we would not have kept the absolute value, then we would have found an error and we wouldn't have been able to solve this one. So we simply solve for c, and we end up with c being 1. My constant is 1. So the differential equation is simply y is equal to x minus 2 times the ln of the absolute value of x plus 1. Done. Note, every example was an indefinite integral. However, the process is the same if we're asked to evaluate a definite integral. Okay, so everything that I've taught you is similar to the definite integral. However, don't forget that if you're evaluating in terms of u, and we've done this in other videos, when we evaluate in terms of u, we need to change our new, or we need to find a new upper and lower limit. And we're going to do one example of that here. So let's evaluate the definite integral of 5 over 3x plus 1 from 0 to 4. Now, we're going to factor out the 5 as a constant, and we end up with 1 over 3x plus 1. However, if I were to take the derivative of 3x plus 1, I would end up with 3. So we have a small problem here because my numerator in this case is simply 1. So I need to change the look of this function. So I take the derivative, I end up with du dx equal to 3, cross multiply, and solve for dx. So I end up with du over 3. So far so good. Now, I write this in terms of u. And because I'm going to evaluate this in terms of u, I need to find my new lower limit. How do we find a new lower limit? Well, originally in terms of x it was 0, but now I'm going to replace 0 into my u function, which is 3x plus 1, and evaluate. And I get my new lower limit, which is 1. Then I need to find my new upper limit. So originally it was 4. Now I evaluate when x equals 4. 3 times 4 plus 1 is 13. So my new upper limit is 13. The reason why I'm doing this is because I'm going to evaluate this integral in terms of u. So now my new limits are 1 to 13. I find the antiderivative. I use the fundamental theorem of calculus, f of b minus f of a, evaluate, final answer 4.275. And there you go. And last but not least, practice, practice, practice. Like the way I end every video, you have to practice these techniques to get a lot better at it. So don't forget the U-substitution, extremely important. Remember to use the logarithmic integration, especially when we have the form u prime over u, or of course, if the degree of the numerator is larger than the degree of the denominator, we need to use the process of long division. There you go. Enjoy.